Okay, good afternoon and thanks a lot. And what I like to do today is walk you through to why high concentration photovoltaic will be the primary choice for large scale solar electric generation in very sunny climates. Am I doing something wrong? Not moving. Yeah, it's green. There we go. No, it's not moving. No. One more. There's another one. There we go. Thank you. Why high concentration photovoltaic? It's, electrons, kilowatt hours, whatever we have, whatever we produce to generate electricity, it's always you're looking into the lowest price. So the primary purpose of high concentration photovoltaic to get the lowest LCOE. So high concentration photovoltaic, it really gives you that. And low LCOE, it has exceptionally high performance because you're using very, very sophisticated, high efficiency solar cells. And it has a very small footprint because you have a very high efficiency as a system. Therefore, the footprint is very small. And it has several other things going for it, like very rapid deployment, because earlier we heard one of our presenters said that the field is very important, how you put things together very quickly. And most important of all, it requires very low capital. I'm going to talk about every one of these subjects as we go along. So, per Lammeyer, it is very, it has obviously look into every one of the LCOE, which is levelized cost of energy, and you come to the conclusion that high concentration is the lowest levelized cost of energy of all other PV technologies at this point. As I said earlier, you cannot use high concentration everywhere in the world. Usually, it is performed the best, or you reach its best potential in very sunny, high insolation areas. And you could see on this world map over there where are the sunny and high insolation areas, starting from California, Southwest, and to the North Africa, South Africa, and to Australia, and so on. It works very well. It even some medium insulation areas, but it doesn't excel as much as it could when you have a very sunny and dry climate. So as I said earlier, it is the best choice for larger scale solar electric generation because it has a flexible deployment. You could deploy those from 1 megawatts to hundreds of megawatts. It's in steps. It's very easy to deploy, and it has a minimum consumption of water. Well, sometimes this particular slide is comparing on larger scale solar electric generation with CSP, and that's why we're talking about the water and we're talking about the deployment. And environmentally, it's very friendly because like Amonix's products, they sit on pedestals, and therefore they really don't shade anything, and you could graze underneath of it, and animals walk around and everything else. So kind of environmental because you have a one pedestal sitting in there, and you have like 60 kilowatts, and tracking on top of that. This is what I think is one of the most important facts, because the high concentration, setting up high concentration factory, it is 1/3 to 1/5 of any other PV technology. It usually costs you between 40 to 60 cents per watt versus several of other polysilicon or thin film that cost much higher. And as you go in the world and as you're trying to deploy those, it is very easily, you could see that people don't have infinite amount of money, and the investment firms and investment companies, they really value their money, and therefore could make a big impact of how much you're going to invest to set up into factories and to set up production. And basically, as I said, high concentration photovoltaic, it is very, very, very low in like 30 to 60 cents, depending on whether you include the cell in there or you don't. If you don't include the cells, it's about 30 cents. If you include the cell, to about 60 cents. So that's a very big factor. That's what we think. That's what this particular technology will be a dominant in the years to come in the larger scale solar production. Now, the journey to CPV is said. Obviously, it started with a concept, and most of you understand what a high concentration is. It's basically, it's very simple. Like all of us, when we're a little kid or something, we always use a magnifying glass to burn something. It's and it's evolved from that into capturing the sun's power into phase one, which is the science. And lots of people, many people worked on the science part of it, is trying to develop it and to use its potential. However, in the early years, in 1980s, 70s, and things, you didn't have a particular cell that could withstand the rigors of high concentration. And it's impeded, it's, lots of promises, lots of broken promises. However, with the advent of availability of the cells and with that on the technology, things start happening. In around the 2000 to 2010, we have the cost, reliability, efficiency gain, which is we call in the commercialization phase of it. And our company, for example, we put like we work on the technology phase for 7-8 years, and then subsequently between 2000 and 2010, we deployed lots of them in the field to learn about the reliability of it, to learn about the durability, and to learn about energy generation, prediction, and all those, and the cost, and what it takes to get this into larger scale. And finally over here, we come in the current phase over here, which is the market segmentation, and that's why Amonix decided to go after the larger scale solar electric generation, and we don't put anything in the small scales like homes or anything, because I don't think a concentrated technology, it adapts itself as well to those kind of applications. So that's why we've chosen to do utility scale, and that's what we're going after. So I'm going to give you a little bit overview of Amonix. Okay, Amonix started like 1989 with the vision of to make low-cost solar electricity for the masses. At those days, the electricity was, from the solar, it's very high price, and it's hardly we're using it on Earth in terrestrial application. And I used to have another company that I use solar cells for the space applications in that one. And basically, I decided that we're going to have to do some kind of technology that yields itself to generate electricity from the sun for the masses. And it's been a long journey, and so we have over 16 years of real-world experience in this field. And believe me, it takes lots of experience whenever you're introducing new technology in the world. Usually, it takes lots of experience and lots of proving in the field. And so we think that today the building in the middle is our headquarters in Seal Beach, California, and we have been working with many utilities and developers, and this kind of gives you a picture of what we started R&D in 1989 to 1992, and from there we made what we call a stubby over here that we proved the concept, and it's so on, and finally what we have today in 2011, what we call our 7700, which is 60 kilowatt unit with over 27% efficiency. That's what we're deploying in the field at this moment. Okay, as you see in this chart over here, that's high concentration our product, Amonix's product at this point, it has a very, very high efficiency at systems level. It's at system level at AC. It has over, in production, that is not one of them. It's between 27 and 29% efficiency. And it is the most efficient solar electric generator in the world at this point. Okay, and another attribute, because of its compactness, or let's say small footprint, it has the highest energy generation per given acre or given area. One of the attributes of high concentration is the matching the load. And as you see in this particular slide, that's the demand is on top. Oops, what did I do? This doesn't go. Here you go back. Okay, the demand on the top over here, and you see that this is comparison of different technologies because of inherent, tracking that involve in the high concentration. Without tracking, high concentration will not work, obviously, because we have to track the sun and you have to be perpendicular to the sun all the time. Because of that, which is built in and comes for free, we generate much more electricity, especially in the peak afternoon hours. And this particular slide shows you that high concentration, because they use multijunction devices, they're very, very well suited for very hot areas, climate areas. The reason for it, because multijunction, they have less sensitivity to the temperature changes. They basically have about 0.16% per degree C versus like silicon, crystalline silicon is 0.4 to 0.46. So it is very serious, so you don't drop drastically in the very high and hot areas. So that is very big plus for high concentration to work into very sunny and hot areas. So my primary purpose of my presentation today to show you that this technology has been coming along and it is competitive today and has a plenty of headroom into reducing the cost drastically, where you could make high concentration technology is, let's say, with grid parity. I don't want to say grid parity because everybody understands grid parity with from different angles. They approach it, they understand it differently. But it has the potential going between 6 and 8 cents kilowatt hour in very quickly. Okay, and basically, what shows over here, kind of the history in our case, about 15 years ago, we had a 7 mega module system that is about 70 feet long and 48 feet high, that did 35 kilowatt. With the advent of the multi-junction devices, which is today like 40% or so, they've gone into 60 kilowatt right now with producing what's lots of improvement that we foresee to go 75 kilowatt or 80 kilowatt for the same system next couple years. So the technology. Okay, the cell technology itself, as I said earlier, you're using very, very, very sophisticated high-efficiency solar cells, what we call right now triple junction, multi-junction solar cells that many people that produce, like people like Spectrolab, EMCOR, and Azure, and there are about 17 more companies that are startups. They're trying to make this cell and excel in there. And in this particular field, everybody is striving to make higher and higher efficiency in that one. So as you see, from my tenure, last 10 years, the efficiency of the multi-junction solar cells have gone up 1% per year. Right now, they're at 40% efficiency. Okay, that's in production. Obviously, lots of people, like recently Solar Junction has announced 43.5% efficiency in a Champion cell. Spectrolab has 41.7. Everybody has something different, but in production right now you have 40% efficiency, and it is promised to go for 48% efficiency in the next let's say it's about 4 or 5 years, but usually we're counting on at least 45% in high volume production on that one. So This one, it shows you plenty of headroom. You don't only get, high performance from the cells and to reduce your cost of your product. Simultaneously, you could take advantage of the fine-tuning to the spectrum. Because you have a multi-junction devices, usually you have lots of different spectra. It will change, the performance of the device will change with the spectra. Therefore, if you have the capability of tuning them with different areas, and therefore getting more efficiency or more power production, more energy from them. And this slide over here demonstrates some of that. And as you see in here, what we're projecting at this point, that at this point we have in production 31 to 31.5% efficiency modules. They're about 280 watts per square meter. Okay, and by the end of this year will be around 33%, and in production we expect to have at least 32% efficiency, which translates slowly into the system-wise in AC. You're going to lose some into the translating DC to AC. You're going to get 29% efficiency to 30% efficiency system. Now, you have lots of headroom again in the lenses. The lenses we use right now are the optical system. Obviously, there are a couple optical systems you could use, either mirrors or you could use which have reflective, and you could use refractive. In our case, we use Fresnel lens, which is refractive. And Fresnel lenses right now, they're either made from glass with silicone. The lens part of it is from silicone and the glass is the carrier, or you have PMMA material that does the job. We have used both, but we prefer to use PMMA at this point because it's lightness and better optical efficiency. We have achieved 88 to 89% optical efficiency so far, and we count on by much precision manufacturing of the facet, and by putting anti-reflection coating and things to reach up to 93% efficiency for those kind of optical efficiency. I have to remind you that in our system, we use only one optical pass. Usually, every time you use the optics, every time you bend it or go to another optical element, you lose about 3-4%. In our case, we have one Fresnel lens, and directly it's beams, concentration on the cell. Therefore, we don't lose awful lots. That's why we have very high efficiency in that respect. Now, the other thing is every time you use lots of cells, everybody that's in the field knows that you have losses when you combine them. And people like in the flat plate areas, they bin them, like you heard earlier. Lots of binning goes on, different efficiency, different current. In our case too, we bin to some degree, but it's not worth to do it to the nth degree. Therefore, you throw them together to some degree, and you expect some losses in the combining of the cells. And the losses could be substantial, could be anywhere between 4 to 8%. And you could mitigate some of those. Right now, what they have what's called the microinverters, and we're doing a lot of experiment with those things. And you could see that with the microinverters, you could maybe gain another 4 to 6% in the energy generation again, kilowatt hours. Another, this is showed a picture. This is in Solar Tac in Colorado. That's in the back of it. All this is about. There are about 500 microinverters carried at the back of the each one of the receiver plates, what we call them. So you could expect about once they've implemented, lots of people work in the microinverter area, and there's lots of ways of incorporate them right on the cell, close to the cell itself, make a hybrid out of it. Right now, they're discrete little boxes that we have put outside just to realize what the potential of those are. So supply chain and maturation and volume manufacturing, like every particular technology in the world. Anything is new, and you have to develop the supply chain. And the supply chain in our case, obviously, we're now producing at 50 to 80 megawatt level. And imagine as you're producing it to gigawatt level, that will mature and the price will go down considerably, and it's a 10-15% easily. And then on top of that, as you build into higher manufacturing and going from 50, 100 megawatt to gigawatts, you have lots of room over there to improve on the volume purchases simultaneously. So those two aspects of it is very important because it's a new technology. What I said earlier, again, I keep repeating it, we are right now competitive today. We compete with everybody else in the world right now, and that's why we're getting lots of jobs. And so there's lots of headroom. And that's what I'm trying to illustrate over here, that between the cell, between the length, and between the losses, and between the volume manufacturing, and saying that you have lots of room to grow in that one. And another thing that what we call in the high concentration, it's very important that you track accurately. And if you don't track accurately, you lose energy. So more sophisticated you get into your tracking, and more energy you could harvest. So those are the things, that area that all high concentration people are working on and to improve on. And this, for example, it shows one of the higher, better tracking. You get much better energy in that. So what I'm going to, so I'm saying that lots of headroom again. And one of the areas that has been, most of the people been working on, it is how you deploy those in the field. So from the very onset, because we're in the high concentration area, it requires very precision alignment. Therefore, we decided to do all that, tedious work in the factory, not in the field. So that's what's blessing for us. From very beginning, we decided to make what we call a mega module. And the mega module itself, what it is basically 10 foot by 48 feet long. That fits on a truck bed, as you see in here, that each one of them is 10 kilowatts DC. So we manufacture them in the factory, and we align them in the factory, and when they leave the factory, they do about 10 to 11 kilowatt DC. So they go 5 of them, as you see, piled up on one of those trucks. And when it gets to the field, and we have what's called torque tube, they get lifted and put on the torque tube, and you bolt them down. And the whole next thing you see over here, all 7 mega modules have been lifted by the crane and deposited on top of the pedestal. And about very quickly, in a couple hours, you have 60 kilowatts working over there. It's amazingly fast, and that is very important because as in comparison to the flat plate, that they have to put thousands of flat plates because there's humans involved in it, depositing them on structures and everything else. This is very quick. You go over there and you put all the pedestals one after the other, and you dig a hole and you put it in there. You pour concrete and move on. Then install the tracking heads, and you bring the mega module, install them. The whole process is it's really expedites everything else, and it costs much less than many other technologies. And a lot of improvement in this area that we're trying to work on, and like everybody else in the world is working on reducing the field or the balance of the system, installation cost and everything else. And this one, it really gives us quite an advantage of anything else. Okay. And one of the very important part of our mega module, it is what we call a repowering, which really helps you to lower the cost of field upgrades. And if you could upgrade in the field, that extend the life of your installation and therefore lower the LCOE. And this one shows, because our mega module, that's huge. You could go in the field, remove one of the receiver plate and put a new one in there, and it's very easily. And it's only, the receiver plates is only cost like 15 to 20% of the overall cost. Therefore, you don't have to redo the whole system. You could do only receiver plate, and that way you extend the life of your installation. Therefore, you gain on your levelized cost of energy. So this is a projection from several experts and lots of people that analyze our company. And we raised a ton of money last couple of years, hundreds of millions of dollars. And this is projection from them that we're competitive today, as I said, in LCOE. And as we build in volume and sophistication, we bypass the rest of the technologies. So at least that's how we see it at this point today. I'm not saying somebody very smart, somebody is going to come up with another way of making things. Maybe I will tell the same story like I'm telling you today. But at this moment, this is the technology that promises the lowest levelized cost of energy. This is about the system deployment. What I'm showing you over here is we build a factory in Las Vegas, North Las Vegas, and where we created recently at least more than 300 jobs. And we started that one in January of this year, and now it is at the rate of producing 80 megawatts, and by the end of the year we're going to 150 megawatts of production. As you see, it's a huge factory, about 220,000 square feet, and we have lots of robotic automation in there to place the lenses. As you see, a mega module. Let me see this one, what's happened. This is a mega module, and they have robotic lines that this thing goes through. This one places the lenses, which aligns them to the receiver plate on the back side of it. And they come from one end and they go from the other end, and you get on the truck like you showed them earlier, and they get to the field for installation. Those are some of our installations. This one happened to be a silicon installation in Spain, okay, and which was about 8 megawatts, was the largest of its kind in the whole world at that time. This is a 2 megawatt that we recently, beginning of this year, that we installed in Arizona, in the University of Arizona Science and Technology Park. This one, it is in New Mexico. Unfortunately, we were keeping that under wraps so far. I just saw GTI today announced that we have 5 megawatt in Hatch, New Mexico, which is the capital of Chile, and so this is in New Mexico. It just started in operation about a week ago, something, and we're still working to commission it another couple of weeks. But I guess the reporters get hold of things much faster we can. So this is the picture of that installation about a couple of weeks ago, and this one here is a 30 megawatts. Okay, installation that we're working on at this moment. It's Alamosa in Colorado. Most of the people from Colorado, they know where Alamosa is. That is a high plateau. It's about 6,000 or 7,000 feet high. It's a cold but very sunny climate. And we're working with an outfit called Cogentric, which is a Goldman Sachs affiliate. And so they're putting 30 megawatts of this technology. It's, as you see, part of it is done, all the pedestals. And in the far corner here, it looks like those are the finished units. And every morning we get pictures. We have more of it is going on. And very soon that will be installed and will go into operation. So having said that, I go back again. I'm talking about plenty of headroom, because we have from the system deployment, from the technology aspect, from the cell, from the losses, and from manufacturing capacity. And if you put all those in one basket, we could see at least 50% or more of cost reduction over the next 3 years in this particular field. And that's why I'm claiming that CPV is leading utility scale solar for now and in the future. It's basically, we think that the cost of the, I won't call it in dollars per watts, because the dollar per watt is very deceiving and sometimes very difficult, but the industry has adapted dollar per watt because the flat plate. In our case, we talk, basically because it's tracking and thing, we call it the system. So we say each one of the systems, like 60 kilowatts, it does about 180,000 kilowatt hours per year. And so at AC. So we're talking about dollars in, kilowatt out. And we're trying to stick to that one. And we think that we could get the cost of the solar electricity to do between 6 to 8 cents next 3 years. And that's end of my speech, and thank you very much. Okay.